Okay, let's get started. We reviewed the history of reliability engineering, and there are three different approaches to reliability. First one is hardware reliability. Second one is software reliability. And third, the last one is human reliability. In this course, we'll cover only part of hardware reliability. We call it actuarial, not actual, actuarial approach. Physical approach is the structural reliability. We don't cover the structural reliability in this course, but you do better understand the structural reliability, how it is different from the system reliability. Consider this offshore installation. The question is this offshore installation stable against hazard? Let's consider the wind. Consider two extremes. One is low speed wind, about 5 meters per sec. Another one is very strong wind, 50 meters per sec. As you know, 5 meters per sec wind is kind of breeze we can expect every day. But the 50 meters per sec wind has very low frequency. For example, once in 100 years. So the intensity of the hazard, in this case, the wind, has distribution with a different intensity. That means different frequency. So in a graphical sense, we can express like this here. So y-axis is frequency. The x-axis is, in this case, load. So the 5 meters per sec load has higher frequency, and the stronger hazard, 50 meters per sec wind, has low frequency. So we can make a kind of distribution curve for all wind velocity. So you can say that the wind has kind of distribution. Then consider the strength, structural strength of the offshore installation. As you know, for some load, the load is vector quantity. For some load, the structure shows a good strength. And to the contrary, for other loads, it has a low strength. So we can say that the strength is a function of uncertainties in materials, welding, fabrication, assembly, and installation, and so forth. So strength itself has a kind of distribution, just like the hazard distribution. So we can express the distribution of the strength like this. So if we impose the two distributions, there is a situation where the load is greater than the strength. So that means the strength, there is a possibility that, because it has a distribution probability, there is a possibility that the structure strength is lower than the load. That means the structure cannot withstand the load, external load. Then the structure will fail. So then we call it, there will be an accident. So the reliability of this structure is defined as, the reliability is the probability. PR means probability that strength is greater than the load. This is a kind of criteria for the to the stability of the structure. Is clear to all of you? Yeah, it's very clear. So this approach is mainly used for reliability of the structural element. As we know, the strength of the structure will decrease with time. We may call it aging of the structure. But the external load may keep a constant level. But sometimes, ultimately, the structure's strength is lower than the external load. Then we will have fail. So we call the event that the structure cannot withstand the external load. It's called a failure. So in a couple of weeks, you will learn about fault. So we will distinguish fault from failure. Failure is an accident, and the fault is just the state, a failed state. For the moment, it's enough for you to distinguish two terms. The two terms, failure and fault, are different. But consider the offshore installation is very complicated, consisting of numerous components. So the question is, we can analyze the stability of the structure through the structural reliability analysis. But is the physical approach applicable to the reliability analysis of an offshore plant that is composed of many components? So it's really impossible. So reliability of an offshore plant is affected by many components. For example, the reliability of producing oil and gas are a function of the reliability of first equipment like compressors, pumpers, or the heat exchangers, control loops, and the safety systems, including fire and gas. FG means fire and gas detection systems, ESD, emergency shutdown systems, and also affected by utility systems like electrics, generators, steam, cooling water, heating medium, blah blah. There are other. So the reliability of the offshore plant is also maintained by human factors like maintenance. So how can we analyze the reliability of the offshore plant? So we will take actuarial approach. That approach is completely different from the structural reliability. And the structural reliability is very popular in academia. In every mechanical or civil or the aerospace engineering department, there are 2 or 3 professors who had some experience in structural reliability. But in real world, in industry, structural reliability is not that popular. To the contrary, there are few experts or professors in academia who has expert at their system reliability. But in real world, in industry, in engineering field, all the plant and the systems are based on their system reliability. It is the case even for the automobile industry. You may consider that the car itself is kind of a system. So our first interest would be when the car will fail. When will the brake system of car fail? So that is a very serious question. So The system reliability engineering is real world is directly related with the quality of the product. The system reliability has been widely applied to in real world, but the structural reliability is not that useful in real world. You may easily expect the reason. If we know the external load, it's not that challenging thing to design a structure. So in a world of structural reliability, the most important question is to find out the external load. If we know the external load, then the design of the structure is not that difficult issue. But structural reliability itself cannot answer the question, what is the external load? What is the design load? So, for example, in offshore industry, the design load of the structure comes from the process, fire and explosion load. So the structural engineer cannot find their load from fire and explosion. It should be supplied by the safety engineer who has some experience in process and safety. So in aerial approach, in other words, in system reliability engineering, we don't express the load and strength in an explicit way. We consider only the lifetime. We estimate the reliability of the system from that of its component and the configuration of a component. So we have system and the component. So we consider the reliability of the component and their configuration. Configuration means the logical connection of the component. From the reliability of the component and their logical configuration, we can estimate the reliability of the system. This is the basic philosophy of the system reliability engineering. So we don't mind the detailed structure of each component. So we don't know the detail of the one component. So we can call the actual aerial approach system reliability approach. If necessary, we take the component as a system and analyze the its reliability in the same way. What I mean is that, consider this example. What is the reliability of a car? So the reliability of a car is a function of the reliability of an engine, the reliability of maybe wheels, the reliability of brake systems, the reliability of a control system. So we can express the reliability of the car by the reliability of component. So if we know the reliability of the component, we can estimate the reliability of the whole car. Then the next question may occur in your mind: how can you estimate the reliability of the engine? Then we apply the same principle. We decompose the reliability of the engine into several components, like cylinders, fuel supply system, and control systems. So if we break it down and down and down, finally we have a kind of component reliability. They can be obtained through test or real-world data. This is the approach of system reliability. Any questions? So how can you measure the reliability of a component? So in system reliability engineering, our interest is focused on the lifetime. Lifetime is over the mean time to failure. So time to failure is the time between the new component installation and the failure of the component. So time to failure is 6 months. It's kind of period. If you take the reciprocal of this component, this value, you can say the failure frequency is 2 times per year. So they have the same meaning, same implication. Randomness of mean time to failure. Sorry, time. It's a typo. It's time to failure is TTF. Sorry. We'll use this term, MTTF, mean time to failure, time to failure, TTF. So failure is a random phenomenon. What I mean is we don't know exact value of the time to failure. Consider the lifetime of, for example, the electric bulb. From our experience, we know the mean value, but we don't know when our bulb will fail, cannot send the light. So time to failure of the engine and lifetime of we humans. So we don't know the lifetime of ourselves, but we know the average value of our lifetime. For the time being, it is around 72 for men and 75 for women. So I have around 30 years left. In an average sense, you have a longer, ladies have a longer, but I can be killed, possibly even today. But my lifetime is kind of in an average sense. So, as you know, the average came from the observation of a sample containing sufficiently many. So we have a kind of distribution. So you may know about the probability theory. So we express the distribution of the lifetime by probability distribution function, and the mean value of this distribution function is called MTTF, mean time to failure. In terms of human age, we can say that mean time from birth to death. Okay, in short, lifetime. Here is a graphical representation. This is the probability density function of men. I'm here, around 40. So we may have a kind of distribution function. Unfortunately, some Some are killed at early stage, so babies can be killed because of their low immunity capability. Some can live more than 100 years. So we have a kind of distribution. So you know the theory of probability. So the meaning is the fraction whose lifetime is between 30 and 40. Then in order to calculate this value, the approximate equation is 40 minus 30. So the interval is 10. Multiplied by this frequency gives 0.1. So we can say that 10% have the lifetime between 30 and 40. This is the meaning of probability density function. So I used the terms like systems, subsystems, component, items. So let's redefine the terms in a more strict way. System can be broken down into several subsystems. So system, subsystem 1, subsystem 2, subsystem 3, and the subsystem 4. And the subsystem can be split down, subsystem like this. So in a practical approach, we divide the whole system into subsystem and break down the subsystem into component. So we have system, subsystem, and the component of a subsystem is called component. But we usually, in system reliability engineering, we usually use this term, item. In Korean pronunciation, item. Okay? So what I'm saying is that system and item are a kind of official term. Subsystem is a kind of convenience term for convenience. Okay? What I mean is that we use the term subsystem because our brain is not that smart. So it is convenient for us to divide the whole system into subsystem. And then again, we focus on a subsystem and it breaks down into component. But in system reliability engineering, only two has meaning, subsystem and item. So if you find this term, item, you may regard it as component. Sometimes we use subsystem, but the term is only for convenience. The system reliability engineering is effective in Jungwon's term, useful for enhancing the system's safety, quality, and operational availability. And it has great value in the design stage than the operational stage. So you may know this wording, proverb, all is well that ends well. You don't know? It is kind of proverb. In Korean, 끝이 좋으면 다 좋다. Okay, it's our the emotional response to some tasks or to the real world. We even though we have difficult times during the process, if the result, the outcome of it are good, we thought, yeah, it was good, it was excellent. Even though the procedure was excellent, but the outcome and the consequence is not good, we feel that, oh, it was bad. But in design a car, design an offshore plant, design a complex system, always well, that starts well. The system configurations should be carefully and intentionally designed correctly in the early stage. In the later stage, it's not cost effective and economical to change the design. So you should be careful in the early stage. And the proper tool, one of the proper tool is system reliability engineering. In operational phase, we can also apply the system reliability engineering to evaluate the system operability, like how many days we can produce oil by operating the plant. How many days how much energy we can produce from a power plant. And we can apply the system reliability engineering to maintenance. For example, some equipment, consider the failure of equipment. For example, the brake system for car. We can fix the brake after we find some failure with the brake. That means we have a kind of accident. Then we replace the brake. Another smart approach is that we can replace the brake of the car before we are faced with a terrible accident. So two approaches is called the first approach is called corrective maintenance, maintenance after accident. The latter approach is called preventive maintenance, the maintenance before the accident. So then how can you apply the system reliability to the maintenance? We can ensure that we can estimate the risk of each component, failure of each component, and we can see the economic loss for the maintenance. Then we can optimize the maintenance of the system. So we can apply the system reliability engineering to the maintenance in the operational phase. So system reliability engineering has been applied to many areas, including risk analysis, environmental protection, quality control, optimization of maintenance and operation, engineering design, verification of quality and reliability. So you may hear about Six Sigma. Six Sigma is very popular in the industrial areas, and actually Six Sigma is a short version. I can say the degraded version of system reliability engineering. Personally, I don't like Six Sigma. If we understand the principles of system reliability, you can understand everything of Six Sigma. But in real world, the company management first the employee to adopt the Six Sigma without teaching the principles of system reliability. So I don't think the outcomes or performance of Six Sigma is that impressive. Now you are very familiar with this figure. We have hazard, and the hazard will lead to accident, will cause accident, and the accident will have many consequences. And we have safety systems. One is preventive safety systems. The other category is mitigating safety systems. I will show this slide again and again. And how can we apply the system reliability engineering? The analysis about hazard to accident are called causal analysis. The analysis from accident to consequence is consequence analysis. In academia, in university, we learned a lot of consequence analysis, like structural analysis, computational fluid dynamics, and mechanical analysis are all belong to consequence analysis. It's based on we have some accident, so we can say that the boundary condition is clear, and we can solve the governing equations like the equation of motion, energy conservation, mass conservation. Then we can analyze the consequence. So industry, academia is expert at this area, but another side of the story is causal analysis. How an accident can be developed from hazard. So we can apply fault tree analysis, reliability block diagram, and FMSA. These are all tools developed in the system reliability engineering. So if you wanted to be a good engineer, you should know two sides of the story. One is causal analysis, the other is consequence analysis. And this is about models and uncertainties. No model is absolutely correct. No model is correct. In particular situations, however, some models are more useful than others. So we should employ some model to analyze something. The model should be sufficiently simple to be handled by available mathematical and statistical methods. If the model is complicated, it can be written down on the paper, but it's very hard to apply to real world. But the model should be sufficiently realistic, sufficiently detailed, such that the deduced results are of practical use. So the model should be detailed enough so that we can see the action or reaction of the systems. This is the typical way we are doing in system reliability engineering. We have a model. It's kind of equation of motion, carbon equation, and we have data, real data. If you combine the model and the data, we can estimate the reliability. Then we can make a decision. If the reliability is low, we can improve the reliability of component, or we can change the configuration or the logical connection of the component. So the issue is, how can you construct a model and how can you get the precise data? This is a big issue of system reliability engineering. So for the model, we need to simplify the real world. It is the same for all the all the analysis. And to collect the data is more challenging from my experience. How can we, for example, how can we know the reliability, failure rate of the bulb? Then we can test the lifetime of 100 or 1,000 bulbs. But how about turbines, lifetime of turbines? So those kind of turbines are not that common equipment around us. It is employed by some special companies, owners like a power plant owners or the big companies. So to collect the data of the component, a big component, is challenging. These days I'm working on some LNG systems, so I need a failure rate for LNG pump. But the LNG pump in Korea are installed in only in some special companies like KOGAS and the LNG terminal owned by POSCO. So they don't usually report the failure rate because it can be considered that the failure rate, the failure of the equipment can be the weak point of the plant. You can understand me? If they report that our pump fail twice every year, and we spend about 3 days to fix it. So that kind of information is kind of information about their weakness. Say they are reluctant to reporting their failure rate. So it is not that easy to collect the data. So usually we use generic data. Generic, not general data. Generic data is kind of we can collect in a sample containing many components. They are called generic data. This is the end of the part we should finish. We should have finished the last class. Today I will show something you don't like. It contains some equations. So you should understand the equation by heart. You should understand the underlying meaning of the equations, failure models. Reliability measures may be reliability function. We will denote it by RT, reliability. So RT means reliability function. Failure rate, mean time to failure, MTTF, mean residual life, MRL. So if you open the book written by Professor Lawson, there are some detailed explanation. So reliability of a single item that is not repaired when it fails. So reliability is applied to the item, and we don't fix the item if it fails. Like electric bulb, if the electric bulb fails, we just discard. So we apply the term reliability only to the unrepaired item. What do you do if your car fails? You discard it? It's too expensive to to discard. So we usually fix. We usually repair it. For those kind of items, we use the term availability. So availability is a combination of reliability plus maintenance. So maintained item, for maintained item, we use the term availability. So reliability is applied only to the item that is not repaired. So what is T there? T is the lifetime. Consider the human life. Okay? T is the lifetime, the time when the item is okay, the item is operating. So there are many models to express the life distributions. So I don't think these distributions are strange to you. You may be familiar with these distributions like exponential, gamma, variable, normal, log normal, Birnbaum, Soder's inverse Gauss. These distributions, you're not familiar with this, but normal distribution, you are familiar with normal distribution, okay? And log-normal distribution, I guess you are familiar with these distributions. Other distributions is just distributions which have different shape. Binomial, Poisson, geometric. I recommend you should take the probability and the statistics course for any reason. For system reliability, you need the knowledge of probability and statistics. But for any other purpose, you should understand the first principles of probability and the statistics. So I strongly recommend you should take the course. The meaning of time is different from item to item. Consider the structure. For structure, the calendar time is the time. The time, the most natural time to us is the calendar time, the clock. Okay. Another thing like electric bulb. If you measure the lifetime of electric bulb, the calendar time is not proper. That we should only consider the time when the bulb is light, when the bulb is sending light. So we should only consider the operating time. So calendar time has no meaning to the bulb. We only consider the operating time when the bulb is light. How about car? Yeah, we should use the mileage. How many kilometers the car is running. Switch. So when you consider the kind of time, the correct way to express the time may be the frequency. How often should I push to make it fade like this? Bearing, maybe the operating time will be the correct time. So what I mean is that the meaning of time can be different from item to item. So you should choose the correct time. In industrial world, sometimes it is very confusing. For example, the operating time is meaningful to electric bulb. How about pumps? Operating time can be critical, but we know from our experience that if we stop the pump for a long time, the failure rate can be increased. So we, mankind, don't know well about all the detailed structure of failure. So usually they report both times, calendar time and the operational time. So the user should choose between the two times. Distribution of time to failure, lifetime, is random. You know the meaning of random. We don't know exact time of occurrence. And the distribution is continuous, and it can take any value, and approximated by a life distribution. So there are some equations you should understand. I think it's the only one class I show you some equations, so you don't worry about the mathematics. I usually don't try to teach something that you can learn from textbook. Okay, you can learn it from the knowledge from textbook. It's a kind of waste of time for me to teach about that, to rewrite the equations or something else. So I want to teach you the principles, how to apply it, and how can we interpret the result of the. So FT, here we have capital FT, larger, let's call it large FT, small FT. So you should distinguish probability density function from probability distribution function. They look similar, they sound similar, but their meaning is different. Probability density function. Small FT is a density function. So density function always has a shape like this. Probability function is integral of the function. So let's find that. So probability function has meaning. Probability density function actually has no meaning. It's not that apparent. Large FT means probability that large T is less than small t. So what's the large T? Large T means lifetime or MTTF. So for our case, it's a lifetime of ours. It is 0 to t integral of small ft. So if ft, t is 40, the meaning is the probability we can live until 40. Okay, we will, the probability that we will be alive, not die until 40. It's the meaning of large ft. Small ft is just derivative of ft. So the meaning of, it's the definition of derivative, so I don't have to repeat it. So the physical meaning is important. Probability that t, large T is greater than t and smaller than t plus delta t is approximately to ft plus delta t. You may remember this 30, 40, okay? So this is ft, probability density function, and the probability that we can live between our age, our life expectancy fall between 30 and 40 will be 10. 10 is delta t times ft, maybe 35. Then the probability that the life expectancy fall between 30 to 40 is approximately expressed by 10. 10 is delta t times ft. ft is the value, maybe 35 is 0.1, maybe 0.001. Can you distinguish ft and large ft and small ft? It's the ABC of statistics. Okay. So we should check this. So this is the density, the frequency. Okay, frequency. Ft, small ft is frequency. Okay, large ft is the accumulated frequency. So area under ft is 1. The sum of this area is 1. Area under ft to the left here is, for example, let's take a 0.5. The area, this area, is large ft. Area under ft between T1, T2, let's take T1 and T2. So area between this area will be expressed by this equation. We have 100 person, and after we observe the life expectancy of these 100 people. Some will die. Two people killed when they are less than 10 years. Also, some are 10, 20, 30, 40, 50. Some are killed, some died when their age is between 10 to 20, maybe 3. So we can construct a graph if we know their life expectancy. Ellen, can you understand? Yeah, it's very good. Let me explain in Korean. Okay? 100명의 사람이 있어요. 100명의 사람을 우리가 쫙 관찰했어요. 언제 죽는지. 그래가지고 우리가 막대 그래프를 그린 거예요. 10살 미만에 죽은 사람 100명 쭉 보니까 2사람이 죽었어요. 10살에서 20살 사이에 죽은 사람 세보니까 3사람. 20살에서 30살 사이에 죽은 사람 7사람. 쭉 이렇게 그릴 수 있죠. 그럼 이런 막대 그래프가 나오겠죠. 이게 다 해서 100이니까, 100명이니까, 우리가 다시 100으로 노멀라이즈 하면 확률을 구할 수 있죠. 그러니까 10에서 24에 죽을 사람 100으로 나누면 0.03이잖아요. 그렇게 그린 게 뭐예요? probability density 펑션이에요. 그렇죠? 그래서 여기서 만약 10명이 죽었다면은, 그렇죠? 30에서 40 사이, 뭐 10명이 죽었지만은 확률 함수로 그리면 얼마예요? 빈도 덴시티로 그리면은 여기 100으로 나누면 0.1이잖아요. 이렇게 되는 거죠. 그래가지고 이제 그릴 때 뭐냐면은, 그러니까 30에서 40 사이가, 그러니까 FT는 뭐예요? FT라는 것은 30살까지 산 사람들 다 합친 거. 그렇죠? F60이란 말은 뭐예요? 60살까지 산 사람 다 합친 거. 예, 요런 뜻이 되겠습니다.
죽은 사람이 아니라 죽은 사람을 다 합친 건 아닌가요?
그렇죠. 죽은 사람. 그렇죠. 예. 죽은 사람 다 합친 거. 그렇죠. The meaning of a survival function is that reliability, we will denote it by RT, large RT, reliability function over survival function. So reliability function can be called also called survival function. The probability that the item will not fail in 0 to t, probability the item will survive at least to time t. So it's the complement to failure function. So R0 means survival, reliability. If you think of survival, it's more convenient for you to understand the meaning. R0 means, yeah, it's 1. That the lifetime is greater than 0. R 0.5. Now you know the drill. Okay. This is a little confusing. You know the conditional probability. So meaning of this, you know this. Probability t greater than t plus t delta t. In this case, we consider the death of the surviving person. Okay? Meaning of this equation is that their lifetime is greater than t. On that condition, what is the probability? The lifetime of them is greater than t plus delta t. This equation can be written like this. You know the equation for the conditional probability. This is the mathematical definition of conditional probability. So if we now you know the equations. So the important thing is this one, GT. GT means as t approaches, delta t approaches to 0, the conditional probability. So if you rearrange the equation, you can find this approximation. So the meaning of this equation is that the conditional probability that the large t is greater than t, and the probability that the lifetime is greater than t plus delta t is gt dt. So the mathematics is confusing, but consider the real world problem. Okay. After we are testing 100 people. Let's consider the 100 bulb. As time goes on, some electric bulb will fail. The people will die, but for a moment, that this is the operating time of bulb. So we check the remaining the number of failed bulb. After 1 hour, we find that failed and not failed. Not failed means okay. We have 100 bulb. After 1 hour, we found one. After 2 hours, we found another one, like this. So the number of unfailed bulb would be 99, 98, 98, 95, like this. So our concern is that we don't care about the history. We don't know the survival rate at this time. Okay? At this time, we have only 98 bulbs. And we don't want to know that how many bulbs will fail in the next 1 hour. This is the question we have in real world. So this is the conditional probability that the bulb survive 3 hours. In this case, t is 3. The bulbs survive even after 3 hours, and we don't know the probability that the bulb can survive another 1 hour. Maybe 20 hours later, we maybe have 48 bulbs. So we don't know the failure rate, the number of bulbs that may fail within 2 hours. That's the question we wanted to answer in real world. As you know, do you think about this curve, the life expectancy of 100%. How long does it take to construct this curve? At least we need 100 years. We should count the lifetime of each person. But as you know, the history of system reliability engineering is less than 100 years. So we never have observed the perfect sample of 100 years. So the question in our daily engineering world is that the estimate the reliability based on the historical data. So this is a kind of definition of a Z. Okay, when we don't know the picture. In this sampling, we don't know the 20 hours. Now we are here. Okay. If we know the historical data, we can estimate Z. This is how we deal with the sampled data. So you should distinguish GT and FT. So you should consider this equation to this equation. So the meaning of this equation is we know the whole distribution and the fraction between t plus delta t. Then we can use FT. In this equation, we only consider the surviving items. They survived certain items, so our sample is not 100. Our sample is 98. Then GT is, so it's the kind of reduction rate of the sample. So please spend some time to distinguish the meaning of two equations. On the textbook, you may see this equation. So you'd better study how the equations are related. This is the real life data, kind of. That GT is the failure rate based on the current sample. This can be considered the death rate of human. In the early stage, the death rate is very high because the babies has low immune capability, so they are killed by some disease. So death rate is relatively high. Then the death rate is decreased because we are healthy, even in middle age. Then death rate started to increase because the senior people losing their strength and immunity. So the death rate tried to increase. In an industrial world, the same phenomena is observed. If we install some equipment or a component, the component failure rate is high because the component needs some time to adapt to the system. So we call it burn-in period. And the failure rate is constant relatively. Then, with time, the component is aged and the failure rate is increased. So this period called wear out period. So this is the typical failure rate we observed in real world. So our focus is on this area, constant failure rate. It is a kind of limitation of mankind. Okay, we in mankind find it very difficult to develop this kind of curve in real world. So the rest part is the kind of some mathematical operation. You know the definition of mean. So if we know the probability density function, t times ft, if we integrate t times ft, it is the mean of t. So it is the average lifetime. So MTTF is the mean time to failure, mean lifetime. So this is the equation we can find MTTF. In statistics, the average is called the first moment. If we integrate t square ft, we call it the second moment. Now you should understand the exponential distribution. Exponential distribution is that the failure rate is constant. The death rate of the survivor is constant. So in this case, we know GT, we know the failure rate, and we know the failure rate constant. And if we use the equation on the table, we can derive other expressions for FT and RT. So the fundamental philosophy for exponential distribution is that the failure rate is constant. The death rate of the survivors is constant. Then we can derive other values. So MTTF is 1 minus lambda, and the variance is 1 divided by lambda square. So you can derive this equation. So you know the physical meaning of constant failure rate. So this is the curve of the exponential distribution function. This is the reliability. Reliability is decreased exponentially. And this is 1 minus lambda t, 1 minus RT. This is the failure probability function. And there are some important values. MTTF, if we MTTF is, in this case, we can put t 1 divided by lambda instead of t, then we can get exponential to minus 1. The value is 0.4. So you should remember this value and the meaning of this value. This is the another distribution function that is sometimes used in this in industrial world, especially for some mechanical component like pumps and compressors. That is called Weibull distribution function. Weibull is the person who developed this equation. He didn't take higher education, but through many experience, he developed this equation. So this is the equation. So the important thing is GT is expressed by alpha lambda to alpha t to minus lambda alpha minus 1. So the challenge is that how can we estimate alpha and lambda? So we can develop many equations, but the challenge is that how can we estimate the parameters for the equations for the models? This is the real world challenge. So for the time being, mankind usually rely on the constant failure rate model, the exponential model. Homework number 1 will be notified through email. So please let the TA, teaching assistants, know if you don't receive the email within this week. And our department has the honor code. That means if 2 or more submit the same solution before the deadline, the point for their homework is 0 to save the TA's efforts, and moreover, they should report to the department. I know the normal practice of Korean universities because I used to be a student in Korean university. We don't feel guilty to show our homework to others, but you should not. Okay? Honor code means you should not show your homework to others, and you should not try to see the homework of others. It's the kind of ethical problem. Let me explain in Korean because it's very important. Ellen, you understand, okay? 우리 한국 사람들의 전형적인 특징이 법을 어기는 사람 봐줘도 의리를 어긴 사람 안 봐준다. 이게 요거죠. 그래서 숙제 안 보여주는 것을 의리 문제로 해석을 해서 안 보여주면은 뭐라 그래야지, 왕따 시킨다고 그래야 되나? 뭐 하여튼 뭐 찌질한 놈, 쪼잔한 놈 이렇게 많이 이제 하게 되는데 이제 앞으로 여러분들이 이제 계속 사회생활 하는데 진짜 중요한 겁니다. 그래서 보여줘서도 안 되고 봐서도 안 된다. 데드라인 지나서는 이제 숙제를 안 한 것보다 이제 해서 내는 게 좋겠죠. 그래서 데드라인 지나고 나서는 데드라인 전에 낸 친구 것을 보고 자기가 그럼 공부해서 내든가 뭐 조교한테 물어봐서 내면은 당연히 이제 디스카운트 되겠죠. 자기 점수는 데드라인 지났으니까 냈으니까. 하지만 데드라인 전에는 다른 친구 거 보고 베껴서 내시면은 두 사람 다 빵점 처리된다. That's all I prepared for today. See you next week.